do the work that you do.
Yeah. How are they going to do it? They need a copy.
I cannot read, that's why.
Oh, okay.
What?
Does this work? Does it work? Why is this broken already?
Teacher, could you have a working?
The direction of comes the direction of force, right?
Little chest. I thought I brought it
Direction
here.
of common force, right?
Oh my god, man. 10. Yeah. Get this. Can you put that first one? My.
I don't want to go there with all those kids.
No one's there.
I'll go with you. Okay.
Nobody's there. No one's here.
Let's switch places.
What's the color like that? Oh, it's so cold. That pause to save some battery. Let's begin. Good morning again. Okay, so since we're done with your chapter 20, we're now going to proceed to your chapter 21, the continuation of your first unit. And of course, you'll have 2 chapters coverage for your first unit test as well. Okay? So before we start anything, let's have a short recap of your previous chapter, which is all about electromagnetic effects. That includes 2 rules. Okay, so we discussed about 2 different rules in the previous chapter. The first rule was your what? The right hand grip rule. The other one is the left or Fleming's left hand rule. Okay, what is again the right hand grip rule represents? We have the thumb representing your current, direction of the current, while the rest of the fingers, magnetic field. What about Fleming's left hand rule? Which one again is the current? Which one is the current? Okay. Second finger or the middle finger? Which one is the magnetic field? Index finger or the first finger? And the top represents that motion. Okay, very good. Now for this chapter, the main focus is to what? For us to identify and know how there's not included, only 3. We have, I want to know what this finger is called? Ring finger. And this one? Or is the other? Is there another name for this? This finger? The smallest finger. Alright. So basically the main focus of chapter 20 is all about magnets, or the relationship between electricity and magnets. Okay? But in this chapter we're gonna discuss about how electromagnet or electromagnetism, okay, induces electricity. Okay? Now to start, let's have your objectives. Okay? For today's lesson, the objectives will be the following. Hopefully we can cover all of them. But first, okay, first we have showing understanding or show understanding the conductor moving across the magnetic field or changing magnetic field linking with a conductor can induce an EMF in the conductor. Secondly, we have describe an experiment to demonstrate electromagnetic induction. And then lastly, state factors affecting magnitude of an induced EMF. Okay? And of course, including your direct and alternating current still. We're still going to discuss about the difference between these two. Here, DC and AC currents. First, let's focus here. What do you mean by the first core or the first objective of today's lesson? When we move a conductor, let's say the wire, or okay, it's either you move the wire or what? Magnetic field or the magnet. Okay, linking with a conductor, you will or you can induce EMF. First, what is EMF again? What does EMF stand for? You still remember? Electro what? Motive force, correct? Just what else is the other name for EMF? Also known as voltage. Or ED stands for? Okay, I'll give you a plus for the answer you gave me. Just and none. Okay, so we have PD stands for? Oh, you said a potential difference. Okay. I thought another said it. Okay, so what is EMF? What does it do?
Electromagnetic force.
Yes, what does it do then? It's a what? Okay. I think you still haven't fully understand what EMF serves for. So in this chapter, we're also gonna further discuss about EMF. Why is it EMF? Okay, and what is EMF? Next, we have described the experiment to demonstrate electromagnetic induction. Well, I have here, or have brought with me a simple device called AC/DC dynamo. Okay, it's a simple simulation device to show how electricity or current can be induced by simply moving what? Your wires or your conductor or moving the magnets. Okay? So to do this, I need someone to demonstrate this with me. Someone who will spin it for me. Okay? So as a result, okay, boom, hi. Can you please come here? As you can see, there's no battery attached here. So everything that you see is purely what? Power.
Human force.
Human force. No battery attached. Okay, so wait before this. Okay, first, notice that this part of the demonstration device has this LED. So there's 4 of them. Unfortunately, one of them is not working properly. Okay, I think some of the connection are dislodged or disconnected. So this here serves as the DC, while the bottom part serves as the AC. Okay, AC what? AC current. On this one, DC current. So observe what happens whenever tide rotates this motor or rotor, whatever you call this. Okay, observe the light bulb or the LED. No. Alright. Okay, thank you. Wait for it. Okay, let's stop there. Let's stop there.
Like, you have to look backward, this one doesn't work.
Okay, wait up. So what did you guys observe? So tide rotated it to this direction, anti-clockwise. What did you observe? Let's start with the AC light bulbs. Alright. Okay. No, these are the. Okay. What do you see? Do you see? See it properly. Alright, thank you guys. Sit down. Alright. Wait up first. Let's start with the forward. Okay, so what did you observe here? Both of them? Light up. Okay. What about here? Only one light up. Why do you think is that?
One is broken.
What is broken?
Not enough power?
Okay, so actually, wait up. Actually, even if this is working, only this will light up. Why? It's DC. Only one direction. Meaning to say the flow of current only goes to one direction, and that direction flows to this side of your LED only, not both of them. Okay, because if you reverse this, what happens? Observe. Wait time. The connection is out. Okay, reverse. The other side. Reverse. Okay. What do you guys notice? The bottom is AC, the upper part is the DC. Okay?
And then we did.
So whenever the rotation changes, this bottom LED still lights up, while the upper part only one lights up. Yes? The explanation is again due to the direction of the current. Okay, thank you. You can take your seat now. Okay? Again, AC current flows alternating. Meaning to say, if the connection of your wire, let's say for example, okay, I will draw here on the board. Okay, let's start with AC. Okay, as we all know, AC does not have positive or negative terminal. Okay, LED. Okay, that's the number switch. So this one is AC. This one is DC.
อะไรอันนี้หรอไม่ลองทำดูหนาลองคุยกับพี่พ่อที่เชื่อคนมันอยู่
เรามีเราไปเลยยังไงยังไง
โน้ตยังใช่ต้นไหนภาษาไทยเราอยู่โอ้
Teacher, do we eat upstairs or do we eat downstairs? There. Upstairs. Upstairs. That's good. Alhamdulillah.
Alright, I already drew one for the AC because either ways, okay, the light bulbs will still turn on. Okay? So the light bulbs or the LED there is built for your AC. Meaning either one or either which direction it goes or either which direction the current goes, they will still light on. Okay? While DC on the other hand is different. Okay? Since DC only works depending on which terminal, okay, the other side goes, okay, let's say for example, this terminal we have positive on the right side and negative on the left side. Meaning to say the current flow will be from positive or from the right to your left. While this one is left to right. So whenever we turn the rotor in one direction, certain direction, let's say this direction, then the current will flow only to this direction, making the other light bulb not working. Okay? Because the other light bulb will only work. Okay, I'll just draw one light bulb here so that both sides. Okay? So one rotation gives us one direction of the current as well for your DC. That's why the other light bulb does not turn on. If you reverse the rotation, well, of course, the other one will not work because the direction only goes to a certain pattern. For this side, for this lamp, okay, there's two lamps, right? For this lamp, the current will go clockwise, while this one go anti-clockwise. That's why if you rotate it clockwise, only that lamp, certain lamp only lights up, okay? And vice versa. While for AC, since it's also built, AC light bulbs are also built in that manner where it works either side or either direction, then it means
Okay, I found this on the web for Ethan. Check it out.
it means, and if we turn it off, hey, it means, I'll just draw it another here.
Hey, so what is it? I don't know. On your iPad?
Okay, it means that for AC, either direction, both of them will light up. Okay? So when you turn it this way, this light bulb and that light bulb turns on. Okay? Same goes with this.
No matter direction, it's still working only, right?
Yes, that's for AC. Okay?
This one DC.
AC.
My goodness.
You will hear
Alright, any questions about that?
I love
We
it.
didn't even start yet. We just had like demonstrations so that you have the idea of how current is induced in your AC or DC motors. Okay? I'll also explain why AC is more efficient than DC when it comes to generating electricity.
แม่
Okay?
แบบว่าเขาพิมพ์อย่างนั้น
Alright.
Wait. 等一下，我在写啊。
Okay, I'm just gonna move slide. Okay, to start, we have this question. What does, again, what is EMF? All you know and you understand about EMF is that it's an electromotive force or a volt. But what is volt actually?
Pushes the electron.
Okay, it gives the push, or it's like a force, but it's not that gives the push to your current flow. So as what I've discussed it before, your voltage serves as the force to push the current flow in a circuit. But to fully understand it, let's have this part read. Okay, who wants to read it? Can you read from there? No. Eva,
EMF
can you read? Clear?
EMF is an abbreviation for electromotive force. When charge flows through a cell, it is given energy by the cell.
Okay, that's it.
Remember,
Why does this do that? Okay, again. Okay,
the
again.
number of joules of energy given to each coulomb of charge that passes through the cell is the EMF of the cell.
Meaning, what does it mean? First, EMF again stands for electromotive force. And when charge flows through a cell, it is given energy by the cell. And the number of joules of the energy given to each column of charge that passes through the cell is your EMF. Meaning, EMF is a form of energy, kind of, that pushes the what? Current in form of column or charge. What is column again? The unit for charge. Okay? Why and how? Example. Do you still remember this formula? Energy is equals to I V T. Meaning to say, energy is also equals to voltage, or in short, EMF. Meaning to say, the reason why current flow because of energy, and that energy, or that energy responsible for the current flow, is called your EMF. It's not a force. It's like an energy in form of force, also known as voltage. Okay? Do you understand that? Meaning, again, it said there that the energy given to each column of charge that passes through a cell is the EMF. Basically, EMF is energy. Clear? Also based on the formula, EMF is energy. EMF stands for electromotive force or voltage. Other name for voltage and EMF is heating. So many names for what? Okay, now let's move on to your main topic. Alright,
PD and E
potential difference.
EMF is I equal EMF.
EMF or voltage or P. Okay? Or that. Given to the charge sounds like EMF. Anyways. Okay. Let's move on. Let's go to this part. Okay. Also interesting part. Now, to induce electricity, so that we can understand why we have lights, our light bulb turns on, is because of energy. From what? From what? from simply having these following parts or following components. So what are the components again? We needed to induce a current. We have a conductor or a piece of wire. A magnetic field due to magnet. And in addition, movement. Of course, you can't just place a wire and a magnet next to each other and expect that there's what? Magic. Okay? You need to have what? Force or movement. Equals to EMF or electricity in short. Okay? In layman's terms or in layman's terms.
Let me figure this out.
Okay, very. Again, ha? You simply move the wire across what? A magnetic field. Okay? Then you can induce electricity already. Now, always remember as well. In this example, which direction does your your magnetic field goes? North to south or from your left to right. Now, how would you move the wire? Let's say you are to move the wire somewhere here. How are you going to move it so that you can induce current for you? Okay, there's two movements. Okay, I'll give you example. Should it go this direction? What is that direction? Side to side. Side to side or
Up and down.
horizontal, what's that? Vertical, horizontal. Oh, side to side. Side to side. Let's just use that. Versus
Up and down.
up and down. Yay. Up and down. Now, which one is the correct way based on the example? Okay, so that in result you can have EMF or induced EMF. Side to side. Let's say this is the magnet. You move the wire like this. Or up and down, move it like this. Which one is the right one? Or it doesn't matter? Does it matter? Or it doesn't matter? Does moving it into different ways, let's say for example side to side or up and down matters? Will it still induce electricity even if you use this or either this? Or only one works? It could be that or that. Which do you think?
Pardon? What's the question again, my good friend?
Again,
Okay, shit.
will moving the wire side to side or up and down matters?
Both are good,
Or moving only one direction will work? Start with that. One direction, yes. If the position of your magnetic field is horizontal. Okay? Now, which one then? Up and down or side to
I think
side?
both is good, no?
Okay, here's your clue. It should always be what? Per head. The-
So it's
So up
both.
and down,
It's
right?
up and down.
So which one?
Up and down.
Up and down.
So that's
Okay?
the mode.
We should always remember their interaction should be at 90 degrees angle, okay, or perpendicular.
The motion of what?
The motion or the interaction between magnetic field and the conductor should perpendicular to each other. Okay? Perpendicularly or right angle. What's that term? Right angle.
Magnet and what, teacher?
Magnet and a conductor for the wire. Okay, the wire and the magnet. So you can either move the wire or the magnet across each other.
For force, right?
That is for movement. Yes,
So
of
it's a
course.
movement for a current to happen or?
For current to be induced, we're trying to induce current here. You need to move one of the two, even, or one of the two requirements. We have the wire or magnet across each other's magnetic field, or each other's what? Field. Okay. Here's an example. Next slide. Okay. On the next slide, I'll show you. There's the explanation. Okay. It said there, the production of EMF by moving a wire in a magnetic field is known as electromagnetic induction. Okay? Actually, didn't say anything there. But anyways, yes, it should be perpendicularly to each other. Okay?
The production of EMF by moving a wire
It's known as the electromagnetic induction. And moving it should be perpendicular. Then move. No. The next slide is.
should be. Wait a minute.
Yes. Very good. Then you get it. In order for you to induce this, you should move it like this. Okay? Not side to side. Should be up and down. That's up and down. Up here, down there. Okay. Clear? Can I move to the next slide? Okay, it's like this, guys. Simple as this. Okay. So here's one example whereas you move the what? Which one is being moved here? Your wire or the magnet? The wire or the conductor. And the direction of the field is horizontal. So how would the conductor go in this example? It should go up and down or horizontal, vertically. Okay? So we have moving the wire downwards through the magnetic field induces an EMF as shown it on a galvanometer. Are you familiar with this device? I've mentioned this before, but we didn't have this.
There is no current and voltage.
Yes. So in this case, the movement of the wire goes where? So it's pointing at, normally it's pointing on the side only, then reads this, and reads like this. But for galvanometer, if we, okay, plus 0.9, minus 0.9. Alright, what's a galvanometer? Measures and both what? Okay, very good. So in this case, you will see that the galvanometer will move from side to side. That is because your conductor is also moved
Side to side.
not side to side,
Up and down.
it's also moved up and down in two directions. Okay, downwards and upward. So this one also moves downward and upward, depending on which direction your current would flow. So let's try and use the rule. Okay, what are the rules again that we have discussed in the previous chapter? We have number 1, right hand grip rule. Grip rule. Okay, on the other one we have Fleming's left hand rule. Left hand rule. Okay. What about this? Do you have any idea? Is it the same? Are we still using Fleming's left hand rule? The answer is no. We're gonna use the what? Fleming's
Right.
right hand. Okay. How to distinguish between right and left? Okay, teacher. What's the difference between right, left, and right? Obviously, your left hand uses your left hand, and your right hand uses your right hand. No. Okay. The answer to that is
I know.
yes. That's
One
it.
for motion,
One for motion. Okay. One for.
electromagnetic.
Okay. All right. Fine. I'll consider that. Okay. Okay. In short, this is for generator. This is for generating or inducing current or generating electricity versus generating what? Motion. Okay, when you try to use motor as, for motion or movement, then we use the Fleming's left hand rule. When you use a motor in generating electricity, we use the right hand rule. Okay? Right hand versus left hand. Okay? So most commonly this is also used for DC motors. Okay, we can still use DC motor to generate electricity, but DC motors are not efficient for generating electricity. That's why we use DC motor for what? For what?
Battery power.
Okay, battery powered motors. While this one uses AC. Okay, we'll also further discuss about this. Probably if we can't finish it today, next meeting. Okay? The difference between AC motor and DC motor is that when generating electricity we use AC. When generating motion or movement we use the DC motor. Okay, what's an example of DC motor being used?
DC motor being used RC power.
RC cars. What about generating AC motors?
Car.
Anywhere.
Car.
AC motors.
AC motor. Car.
Okay.
Car.
An AC fan. We can use. Okay, here's the difference between DC motor and AC motor. Generally, this here we can use it portably. Okay, you can bring it with you because you can power it with battery.
Laptop.
This one you cannot power it with battery. You need what?
Computer.
An actual AC power or current.
So AC motor. Computer.
AC electricity. You need an actual electricity for AC motors. Okay? It doesn't spin. If you attach this to this, it will not spin. It will stop. Actually, it doesn't do anything at all. But if you connect DC to AC, what do you think happens?
AC to DC.
When you connect DC motor to an AC power supply, what do you think will happen?
It might not work.
It will?
get stuck.
You even answered it there in your book.
Oh,
It will
it
only
vibrate.
oscillate or vibrate. Okay? Because the current flows on this side, it makes this flow, it makes the direction of the motor go that side, let's say. Okay, but since it's an alternating current, then other end will also do the same thing. So it's just bouncing off like this. That's why it causes this vibration to your motor. Okay, so it will not work. It will not even spin at all. Okay, again, left hand rule. By Fleming, we have for DC motor or generating motion, DC motor that uses battery. While Fleming's right hand rule, we use it for generating electricity. Okay? Going back here. Let's move on. We're almost done. Okay, number 2. This time you read. Ava.
Moving the wire downward through the magnetic field induces an EMF as shown on the calculation number 2.
Okay, so first we move the wire downwards. And as a result, your galvanometer moves to the left side, to the right side rather, while moving it upward, okay, giving us the induced EMF, which gives us a reading for your galvanometer pointing to your left. Okay, can we check if it's actually, or if the Fleming's rule actually can be applied to this? So, as what you can see, we have movement up and down, direction of the current, or the magnetic field rather, to your left. So using right hand, since we're doing, we're inducing electricity, electricity. Okay, since we're trying to induce electricity here, then we're going to use the right hand, Fleming's right hand rule. Okay, so movement is downwards, while magnetic field is to your left. So I mean to say the direction of that field is away from you. Okay, so that's why the reading is what? Goes this way. Okay. Okay, according to that example. Okay, vice versa, we have upward magnetic field away from you. That's why the reading gives us now this direction. Okay, so how does that work? Just imagine it like this. You're just pulling the string from the bottom. So if you pull the string from the bottom, okay, and the direction goes that way or this way, it will go that way. Okay, So the string will pull the arrow, moving it this way. Yeah.
Can you like what way does it?
Just imagine it that there's a string attached at the bottom of the
7 minutes. Oh.
pen or the marker. When the current flows or move to that direction, the string will pull it, causing it to what? To tilt on this side.
Yes.
Okay? Same goes on the other side. So if you reverse the direction of the current, just pull the string and it will move to that side. So just imagine it like that. Okay? So that you'll be able to identify the flow of current by simply using Fleming's right hand rule. Okay? Any questions? Right.
Moving the so
Now before we
if it goes that way, the gravity will point that way.
now, if it goes this way, then the galvanometer will point that way. We should pull the string down here. Okay?
Wait, just leave it like that. Let me take a picture. Thank you.
Okay, the next one. There. Alright. Now before we end anything, let's have this part. And of course the last part is this guy. Okay, who's familiar with him?
Alright.
Okay, what's his complete name?
Faraday cage.
Last part starts with our M.
Mike Wazowski.
You should know this. You were
Michael
in the class
Jordan.
yesterday. Huh?
Michael Jordan.
This is his family's name. His full name is Faraday.
Mickey Faraday. Michael Faraday.
Michael
Yeah,
Faraday.
see, give me a plus point.
You
Yeah,
didn't
okay.
even give me my point.
You got like what? Negative point. Is that negative point or is that plus?
Fine. No, just plus.
Really?
All of these are plus points. No negative points.
Do you actually record that?
Yes. And at the end of your chapter, I give plus points to your overall result for the work. Some of you might get like couple of these mistakes. But if you get full score for the workbook, I can't give you more than the full score. Right? So I'll just give it to your what? 4 C's for your behavior, participation, and cooperation. Okay, anyways, moving on. So in this part, we will be paying your current, okay? Induced current to be increased, or ways to increase induced EMF or current. So there's 3 ways here according to your slide. I'll put it down. Okay, so to increase induced EMF in your motor, we'll have to either move the wire faster. Basically what? So as what Ty, or me and Ty showed earlier, as Ty speed this faster, the lights or the light bulb lights up or lights up brighter as well. Okay? So the faster you go, or moving it faster, will cause the what? EMF induced greater. Next, stronger magnet. How can we use strong magnets? Or what are strong magnets made of? Iron, or mostly hard magnets. But what do you call to a magnet, to that magnet that is way stronger than the normal magnets? Neodymium. Yes. Lastly, we have increased the length of the wire, or simply what? Adding more coils. Adding more coils in the loop will give us more what? Meaning to say, if you add more coils here, it would give us more energy output. Okay? Any questions? None? Lastly, what's his name?
Michael Faraday.
Michael Faraday. What is his contribution to
Magnetic.
science? Electromagnetic attraction. So basically, he did not discover what? Electricity.
Really?
Along with,
Teacher.
are you familiar with Tesla?
Yeah. Nikola Tesla. He's really.
Yes. Yes, along with him.
Teacher, we have a question. How is electricity made?
We just discussed it again.
Other than copper and force, like how does the machinery work? Does
What do you
it
mean?
use quartz? Does it
The-
use like quartz or something?
Or are we talking about the generators? The
Yes,
big ones?
generator. How does
Well, it is made of the same material, magnet and conductors. Okay? along with it some parts so that it would efficiently rotate or spin. Okay, with that, you can have more efficient output. Okay, of course, those are the parts mainly for the motors. Okay, which will be discussed next meeting. This one, since it's already time, we'll discuss and continue this next meeting. Okay, now in terms of parts, this is how the two motors differs. Just to give you some idea on how they look before we proceed to your next. Okay, so we have the slip ring motor and the split. Which one is the DC again?
DC is the bottom, AC is the top.
You still remember. What's the difference between the two motor? There's only one thing that differentiates the two. The what? The rings. Which one is split? Your DC. Which one is slip? Your AC. What do you mean by slip? Slip. Two separate rings connected to one side of the coil. Slip. Well, simply they are connected to one side only. You need to say this side of the wire, the conductor is only connected to that side whenever it rotates. While this one is connected to the side of your ring as well. So you need to say whenever they change location or side, the current changes as well. While this one are split, whereas whenever they change sides, okay, or the coil change sides, the rings changes size as well. That gives us the direction into one place only. Okay? Because of this ring, due to this ring split together, whenever this side changes to that side, this one changes to that side.
What about this one?
This one remains the same in every rotation. Okay? Giving us this one, giving us this oscillation. This one will only give us a straight line. Okay? Anyways, any questions? If not, I'll give you your task as homework since it's already time. Your homework is on page 208 and until 211. It must be completed by next week, Monday. Okay? Are you clear?
Yes.
Thank you.
No more questions? No. Okay, then that's our lesson. Thank you so much, guys.
Thank you.